Okay, so we're at the flash presentations now, so we've got 5 quick flash presentations. First up, we've got Theo. On you come, Theo. Theo's going to be talking about advanced formulation, mixture rule optimization for enhancing predictability of tablet compressibility and compactability.
I know, it's a massive mouthful.
It is.
Yeah. Thank you very much, everybody. I'm just in the interest of time, I'm going to skip to the end of this presentation just so we can get off to dinner. But my name is Theo Tait. I'm a second-year PhD student here at CMAC at Strathclyde. And yes, I am working on direct compression, just as what Hector was talking about. So, just skipping right to the end. In industry, we have these methods of predicting tablet compressibility and tablet compactability. So that's looking at the tablet porosity and tensile strength. There's empirical models which we use, which are very good at predicting this. I've done quite a lot of work on that in my first year. But the big kind of challenge that we're facing nowadays, and what people have spoken about for the past few days, is the idea about how material attributes and how process parameters come together to impact our quality attributes. So that's what I'm trying to do. So we know that these models can predict the compression profiles and compaction profiles for our blends, but how can we then use them to minimize experimentation when we, say, discover a new API or if we want to change our formulation a little bit? So that's the work that I've been focusing on in my kind of second year, is the idea of using mixture rules to understand the individual components' contributions to the blend behavior. In doing this, I've also developed a new method for optimizing the parameterization of these mixture rules, which is very exciting. And I'm currently working on exploring formulation changes and their impact on, first of all, the quality attributes that we're looking at in tablets, and also the fitter parameters themselves, so we can use them for prediction. So if you want to learn more about this, so if you're interested in these topics, so empirical modeling, mixture rules, formulation development, digital optimization, and smart developmental planning, I'm at poster number 45, and also don't forget to vote for me for your People's Poster as well. But thank you very much.
Okay, next up we've got Diego, also based at CMAC, University of Strathclyde. Something a little bit different. We're going to hear about deep generative models for pharmaceutical manufacturing process design.
Thank you. Hi everyone. I'm going to introduce briefly my project. We are all aware that designing a pharmaceutical process to manufacture a product is very complex task. It's a very complex task. This is why a lot of efforts are invested on developing tools which help us to select the best materials, operation, and conditions. Here, for instance, in primary processing, we can find reaction planners. These, to some extent, can help us to select the best chemical reactions to synthesize a particular molecule. And as these tools, we can find many others which can guide the selection of the best conditions, of the best materials for the manufacturing of the particular product of interest. However, when we want to see how many tools we can find to suggest which is the best change of unit operations to manufacture our particular product, there are not that many options. And here is where deep generative models come into play. Here we can see an example of a couple of very popular models nowadays. Basically, deep generative models are deep neural networks which are capable of generating very realistic samples. These two models, for instance, by providing some instructions, they can generate very photorealistic images that follow those instructions. Now, the idea for this project is basically to adopt these models to our particular task. Instead of providing some generic instructions, we can provide perhaps information about the target molecule or the materials that we're going to use to manufacture a product, and have the model to generate the sequence of operations. What we have done to develop these models at this point is perhaps the most challenging part was to collect the data. At this point, we have gathered data from patents. We have managed to get more than 300,000 procedures of synthesis and purification using natural language processing. With this data, we have managed to train some generative models. Here, this is just to illustrate an example of how this model will operate. Basically, we can have a list of materials, we can have the information about the structure, and basically the model will process this information and can generate multiple sequences of operations which can help us or guide the selection of the best method to manufacture of or final product. I'm going to stop here, and if you have more questions, please visit me at poster number 47. Thank you very much.
So next up's Irene. Irene's going to be talking about understanding solvent-induced mass transformations driven by anomalous mass transfer.
Thank you very much. Yeah, this is just a brief overview of my PhD. So at a glance, what I am trying to do is use a new type of models called phase field models in order to simulate mass transfer and phase transformation in crystallization processes. So you have here on the screen some experimental data coming from the data factory. This is just a binary system, and you can tell that it clearly oils out. So the droplets start being very, very small, and they grow as time is passing. Now, what you see to the right is the evolution that I get with time with one of my models. So as you can tell, it can reproduce the data that we get from the data factory in the sense that I am able to simulate the appearance of a secondary phase that in the form of droplets or nuclei that grow with time. So why should you care about all of this? Essentially, there is a gap in the fundamental understanding on how mixing occurs in crystallization processes. You would think we would understand it by now, but truth is we don't. This is evidenced by phenomena such as liquid-liquid phase separation or oiling out, which is what I was just describing, or Oso effect, or things that were not understood until very recently, such as uphill diffusion. So what I am trying to do is just shed some light into all of this. Now we have here a very basic ternary diagram, just solvent, solute, anti-solvent. You would have your solution feed, anti-solvent feed, and the understanding in this type of processes is that mixing happens along the black line. As you can imagine, this is not very accurate. In real life, what happens is that the non-idealities of your system cause this pathway to deviate. This is crucial because it literally explains what outcomes you get out of your project, out of your experiment, sorry. So depending on what pathway you are following, you're going to perhaps get your desired phase, a different morphology, or even oil out. So in order to track these pathways, you need to develop a robust mass transfer model, which currently we don't have. And that is what I'm trying to do. Now, what models I am actually looking at? If you are in the one-phase region of the diagram, in order to model systems that stay within there, you only would need a diffusion model, perhaps something like fixed flow, which would lead to evolutions of this type, homogeneous systems. Now, if you want to do something more complex, such as going to the spinodal decomposition region, you would need Canhilliard dynamics. I won't go into the equations, but essentially the most important thing is that you're able to simulate phase separation, and that is because you include the interfacial free energy of actually having two different phases. Finally, if you want to take into account what happens in the binodal region, you're going to need Alenkant dynamics. Again, a bunch of other equations. Most important thing is that they allow you to simulate things like nucleation or phenomena akin to nucleation, such as oiling out. So to see some more of my results, you're going to have to come to my poster, because they only gave me 3 minutes, and I'm in poster 49. Thank you very much.
Okay, next up's John. Again, CMAC Strathclyde. Hey, John.
Hi.
John's going to be talking about an end-to-end machine learning framework for the characterization of tablet disintegration in real time.
That is far too long for a title. Yeah, I'm going to go quick because I'm really, really hungry. So thanks to Rachel for giving a fantastic introduction to tablet disintegration so that I don't have to. Yeah, so my work is focusing on a better understanding of tablet disintegration processes, particularly absorption and swelling. So just very briefly, disintegration can often be a performance controlling process in tablets when trying to deliver a drug. So the understanding of this is really important, and it's maybe not as well understood as we hoped, as we hope it should be, but we're getting there. So this, my work highlights a workflow that we can do to analyse a bunch of data from these Cecil drop experiments to understand these processes. So the idea behind this is it was supposed to be a kind of plug-in to Fessel's automated tableting workflow that he demonstrated this morning. The end point of that so far is the Cecil drop experiment on the tablet. The software that I demonstrate is to analyze these videos, extract the data, and give us some parameters that we can then feed into their global optimization so that we can continue the automated tableting process and hopefully make good medicine. So how exactly do we do this? We do it with a mixture of machine learning models. Firstly, we take the video, so a video is just a stack of images. We segment each of these images to pick out the features that we care about. In this case, it's the droplet that we drop onto the tablet. We care about the surface area of that drop, and we can also measure the contact angle as well to tell us about the wettability of the tablet. The surface area shows very clear signatures of absorption into the tablet and also swelling itself. So we want to isolate these regions where these processes are dominant and study that further to understand these processes. Turns out that's really hard to do, so we had to train a deep learning model to find the time points where these regimes change. But once we do that, we can fit our nice mechanistic models to it and get things like liquid absorption rate or the maximum swelling size of a tablet, and hopefully see how these relate to manufacturing conditions, formulation, etc. Yeah, that's all I want to say. I have a poster, number 52. There's also the DM squared demonstrator, which there is now another session added for tomorrow during the first half of lunch. I'm not sure I'm allowed to invite people, but I just have. So feel free to come along to that if you've not had the chance. Yeah, and hopefully the next time we see all this, it should be integrated with all of Fixel stuff. So thanks.
Cheers, Sean. And finally, Martin. So Martin's going to be talking about characterization of a semi-continuous mini blender for use in continuous direct compression. You go, Martin.
Okay.
Cheers.
Hi everyone. Yeah, so I'll take you briefly through the process. So the work we're looking at is kind of related to continuous direct compression, which has been mentioned a few times in this session. And so traditionally you would have feeders feeding into a continuous blender, and that would then feed into a tablet press. So what we're looking at in this part of our project is the use of a mini blender as a kind of additional feature to add to the system, and could be complementary approach. So you would still use the same platform as with the continuous line, so use the same feeders, the same tablet press, but you would replace the continuous blender with this mini blender. So you can see an image of the equipment there. With this equipment, we can achieve a wide range of mixing regimes, as you can see on the videos, because we have a complete independent control over the blending time and speed compared to the continuous line where the two are interlinked. So we've looked at various process parameters in this part of the work, such as loading the API in a kind of corner location and looking at the axial dispersions throughout the bulk blend. We've looked at different levels of API loading, if we can use low dose formulations. We've looked at if there is an impact of the amount of blend we use, so the blender fill level, the headspace fraction, and also some physical properties like particle size of the API itself, how that affects the result and the blending performance. So if you'd like to know more, you can come see me at poster number 54. And as I mentioned, this is a part of the MIC Grand Challenge 1 project, which there's a number of us working on. And so if you'd like to know more about the other parts of the project, you can see some of our other posters. So Hikaru, that presented just before, has poster 42, where he's talking about some of the models. Maria around some of the multivariate analysis that she's done, and Bilal has a poster on the residence time distribution in the blender.